On camera.
Yes.
Start.
Good afternoon, everyone. Welcome to the market session of characterize and non-asymptotics hosted by the Center for Convergence, PC, RBC, IFC. Today's talk is by Professor Siva Theja Maguluri, and he will be speaking on the tale of asymptotics and the non-asymptotics in low balance. Professor Siva Theja Maguluri is Prof, faculty, early career professor, and assistant professor in Milton School of Industrial and System Engineering at Georgia Tech. He obtained his PhD and MS in ECE as well as MS in Applied Math from UNC and BTech in Electrical Engineering from IIT Madras. His research interests are areas of control, optimization, algorithms, and applied probability, and include reinforcement learning, theory, and stress measures. His research and teaching are recognized through several awards, including the Best Publication in Applied Probability, award in Best Paper Competition, Student Best Paper Award, higher performance, Jury Faculty Teaching Excellence Award, and Student Recognition of Excellence in Teaching. We request the online audience to please keep your microphones on silent during the duration of the talk, and you can unmute yourself to ask any questions to the
Thanks for the nice introduction. And I thank the organizers for hosting me on this talk, especially given that there is no learning in this talk. This is pure Q&A talk. So no other venue has been nice enough to let me talk about my Q&A work. So I'm very happy to do that here. And so this is like a very recent work, and this is the first time I'm talking about it. So I'm really looking forward to get feedback and comments. This is joint work with my student Fakir, who is going to graduate very soon, and he's going to start as a postdoc at Columbia Business School, and my former student Daniela, who just started at Kellogg as an assistant. So let's start with so this is a talk on cues. I'm not even trying to motivate because this is a networking seminar. You know, cues are everywhere. Let's start with the simplest cue that we know, MM1Q. So this is a server. There's a waiting area, the arrivals which come according to a Poisson process with certain rate lambda. Let's say the service is exponential with rate mu or rate mu1 here. And if I want to understand the performance of the system, the first question I ask is what is the stationary distribution? And it's very easy to calculate in this particular example, and the answer is it is geometric. And once I know the stationary distribution, I can figure out what the mean Q length is, mean delay, all kinds of things. Okay, very good. Now, as you try to model more and more systems, you end up with more complex queuing systems. And for the purpose of this talk, I'll focus on load balancing system, or this is also called the supermarket checkout system. So there are a bunch of servers, n servers, and each of them, let's for simplicity, assume all of them have the same service rate mu, and each of them has their own queue. And arrivals come according to the Poisson process with rate lambda. I'm using a subscript n so that they can scale it with n eventually. And each arrival should pick one of the queues, and once it goes to one of the queues, it can't change its mind later. And the question is, which queue should it join? And the natural algorithm that we typically use when we're in a supermarket is join short queue. So there's several questions here. The very first question is, under what arrival rates is the system stable? And that's easy to answer. As long as the arrival rate is less than the service rate, the system is stable. And what algorithm minimizes the queue length, minimizes the delay, or maximizes the number of customers served, and it can be shown that join the shortest queue is optimal in this particular setting when you have Poisson, exponentials, and homogeneous service rates. So far so good. Then, in order to understand the performance, I want to know about the stationary distribution under join the shortest queue. And if you ask what that is, the answer is unknown. So I think this is in some sense a limitation of queuing theory. Once you go beyond single server queue, then even some of the most basic questions you ask are extremely challenging. And why am I interested in things like this, finding the stationary distribution? Because when I actually look at it from a practitioner's viewpoint, there are many design questions. How many servers should I employ? In other words, what should the system type be? Or at what load should I be operating? If this is a data center, then the data center provider has service level agreements with customers. And one wants to get a handle on what is the probability that the customer encounters at the queue length of 100. So if I know the stationary distribution, I can answer all these questions, but I don't. So I need to do something else. And so all these design questions have a corresponding analysis questions, which is how does the system behave with respect to the size, with respect to load, and how does the service level change as a function of size and so exact analysis typically corresponds to finding the stationary distribution or some approximation of it. And since we can't do that, we resort to asymptotic analysis. And there are many asymptotic regimes that QA theorists look at. Each asymptotic regime is like a different vantage point, which qualitatively tells us different things about the underlying QA system. And the three things that I mentioned about size, load, and service level, you can look at asymptotic regimes that correspond to each of those three. So if you let the size go to infinity, you get what is called the mini server limit or mean field regime. If you pick the other two and let the load approach 1, then you get the heavy traffic limit because 1 is the maximum load the system can support. And finally, if you fix the service level, if you let the service level go to infinity and ask how the QLND is, you get the large deviation. So these are the three popular asymptotic regimes that are typically studied in QQ. I mean, it's the same picture. I just folded it into triangle. So what I'm going to talk to you today is so I'm going to give I'll present our recent result. But before that, I want to give an overview of various asymptotic results. And so I mentioned the three regimes: heavy traffic, mean field, and large deviation. I'll give an overview of these results in the context of load balancing. I'll just stick to load balancing. And then I'll move on to non-asymptotic results. I'll present some non-asymptotic results on primarily in the heavy traffic and mini-server heavy traffic regimes. And then eventually I'll get to our result and I'll kind of talk about how our result connects to various asymptotic results as well as non-asymptotic results. And if time permits, I'll talk very, very briefly about the proof. We also have some results on other systems, especially GU1Q and Erlang C system. Erlang C is same as MMN, and most likely I'll not have time to. So I was told that whenever you give a talk, you should give the main result in the first few minutes. But then the way I structure my talk, my result is going to come at like, I don't know, 45th minute or something. It was the very end of the talk. So I thought I'll at least flash the result. So I'm going to explain all of these as we go along. So bottom line is that we have a JSQ system, and I'm going to look at the sum of the Q length, the total Q length in the system, and then I'm going to bound this quantity. So you can think of this as if I give you the exact value of this, that is the CDF. I have given the CDF of the stationary distribution, but that I said is impossible. So what I'm giving you is lower and upwards. And notice that there is no limit anywhere. I mean, there are bigos, but there is no limit anywhere here, which means this result is non-asymptotic. So typically, if we go back, I mentioned the three asymptotic regimes. The question is, does one study the MM1Q in any of these asymptotic regimes? No, because stationary distribution has all the information. Whatever asymptotic regime you want, you take the stationary distribution, put the appropriate limit, you'll reproduce that result. In other systems, people look at asymptotic regimes because you cannot find the stationary distribution. Now that I have this approximation of the stationary distribution, I'm going to illustrate that this is going to recover the asymptotic results almost. I'm going to show how it recovers and how it does not recover. The asymptotic results in large deviation and heavy traffic. We don't quite recover the mean field result, but we get halfway there. So I'm going to explain all this. But one thing I want to point out is that instead of looking at the Q lengths, I'm multiplying by some parameter that turns out to be the right scaling in some sense. And then I have upper and lower bounds that are both decaying exponentially. And the exponential parameter, whatever it is, we'll talk more about it as we go along, is the same. Okay. So with that review, I'll jump right into the talk. Any questions so far? Feel free to interrupt me any point of time if you have any questions, because I'm going to present. So I mean, you should think of this as a tutorial style talk because I'm going to present many different results. I'll try to also summarize things as we go along so that you don't lose track of things. So let's jump right into asymptotic analysis.
So just to go back to good. I just want to make sure I understand. So QI is the length of the
QI is the length of the ith Q, and there are n Qs. So this is the sum of all the Qs, and I'm only looking at the sum. And in certain regimes, we'll see that all the Qs will become equal. So if I have some, they're actually going to be equal. We'll see that as we go along. So stochastically, they'll be equal. So they're not independent. So therefore the distribution. So if I have the sum, then I have all the individual distribution. Rakesh?
Just wanted to see the equation whether n is n and how does it go down to 0?
Okay. Yeah, I'm going to talk more about it. Here I just wanted to flash. Okay, cool. So these were the three regimes I talked about. So in this part of the talk, for the next 20-25 minutes or so, I'll basically do a survey of results in all the three regimes. So let's start with heavy traffic. So we said that the stability condition is that the total arrival rate should be less than n. Here I said the service rate is mu to equal to 1. So lambda should be less than n. So I make lambda very close to n. So I pick lambda as n times 1 minus epsilon. As epsilon goes to 0, lambda is approaching n. Then the system is approaching the verge of instability, and the QLFs would blow up. And the question is, how do they blow up? They blow up at the rate 1 over epsilon. So if the gap to the capacity region is epsilon, then the QLF blows up as 1 over epsilon. And then to understand the QLF behavior, you look at QLF, which is of the order 1 over epsilon, multiplied by epsilon, and then take the limit. In the limit as epsilon goes to 0, that is in the heavy traffic limit. This is a vector. This QLF vector converges in distribution to a vector which is all ones multiplied by an exponential, which means there's a single dimensional random variable, a single exponential random variable, and all the QLFs are going to be equal. This is what I was saying just now. So this is the classical limit theorem in heavy traffic behavior of GSQ, and I don't have a proper reference, but references will come later. This was first proved back in 70s or so, Foschini and Salt, but later it has been reproved multiple times with various different techniques, some from our group. And like I mentioned, the key the key thing in terms of behavior is that all the QLFs become equal. I mean, they don't become exactly equal. There's of course going to be some randomness of fluctuations, but they will become almost equal, and that plays an important role in the system. So how does one prove this? So I said there were many different proofs that were done in the literature, but I want to focus on one particular proof called transform method that we developed in my group a few years ago, because the new results I'm going to present build upon this, and I believe it's a lot simpler than other proof techniques that I used to prove this result. So before thinking about GSQ system, let's go back to a single server queue. So this is an MM1 queue, so there's nothing to do. You know the stationary distribution, which is Gaussian, and then you can let lambda go to 1 in that stationary distribution, and you can see what the limiting distribution is. It will be exponential, but I don't want to do that. Instead, I want to develop a new proof technique so that I can use it to study other systems. Or this proof technique can be used to study when you don't have Poisson and exponential and you have other distributions also. Okay, so what is this technique? It's actually very simple. So first you establish that the system is stable, that is, it is positive recurrent, and that can be done using Foster-Lyapunov theorem kind of arguments. I'll not get into it. Once you know that the system is positive recurrent, it means that it has a stationary distribution, and by definition of the stationary distribution, if you apply expectation for some function under the stationary distribution at time, let's say at time k, the q is in stationary distribution, then expectation of some function at time qk of q at time k should be equal to the same expectation at time k plus 1. So basically, the distribution does not change over time. It's a definition of stationary distribution, and I'm using that to look at expectation of a specific function. And the key thing is we pick exponential function. I'm calling this a Lyapunov function. You can also call this as a test function. So all I'm doing is I'm picking my favorite function, setting its drift to 0 in steady state, and I'm working with exponential functions. And once I do that, and this is standard trick. Even if you want to find stationary distribution, you can do this. But the thing is, in the general case or in the load balancing case, you're not going to be able to solve for this expectation of exponential, which is the MGF, which is the transform of the QLF. You're not going to be able to get an explicit formula for this in general. So we look at it in an asymptotic regime, here the heavy traffic regime. So we take the epsilon parameter, let it go to 0. Then we work with the terms. You use just basic calculus, you use the Taylor series and so on to kill a bunch of terms. And in the end, you end up with a transform of exponential. So that kind of pops out of this analysis. And that's how you use transform method to show that in a single server queue, you converge to the exponential distribution. Any questions so far?
Yes. In the result itself, the fact that epsilon qi is 3 epsilon QG. Is that surprising, or the surprise is that it's exponential difference?
I mean,
Because all Qs look to be the same because they have the same service states. So at the end, they behaving, having similar.
so if I do random routing, for example, so I don't look at the Q lens, I come, I toss a coin, join all the Qs. This will not be true. So I'm not saying that the Q lens distributions are the same. That will follow from symmetry. I'm saying the actual Q lens are same. So you stop the system at some particular time, it's following some sample path, right? If one Q is 10, the other one also will be 10. So this is a much stronger statement. And why is that happening? Intuitively, let's say the Q lens are not equal. Then there's some small Qs, some large Qs. I take the small one and send a job, thereby I'm increasing. So I'm equalizing all the Qs in heavy traffic. And the exponential follows because geometric in the limit in appropriate limit converges to exponential. That's the intuition. Okay, so this is a single server queue. Now let's get back to our JS queue. And the key idea is once we establish state space collapse in an appropriate mathematical sense, then because of state space collapse, this should intuitively behave like a single server queue. And so we should get the same exponential. That's the idea behind the result here. So let's dig into this more. So this is the intuition for state space collapse. It's what I just explained, but now thinking of it from slightly different viewpoint. By sending more jobs to the shortest queue, you are increasing it and equalizing queues. Here, let's say there are only 2 queues. I can represent the queue length in 2-dimensional space. Let's say Q1 is smaller than Q2. So this is a diagonal, you'll be somewhere here. Now, anytime there's an arrival, I'm going to send it to Q1 because I'm doing join the shortest. Which means the arrival is going to push the queue length along this direction. And my service are independent. So it's almost in the 45 degrees direction like this. So which means my effective drift of both arrivals and service is pushing me in this direction, which is towards the x equal to 1 line. And so basically I have drift towards this line. And in fact, this is how one actually establishes this state space collapse. That we show that there is negative drift towards this line and on the line. And more formally, the way we show this is as follows. You look at your Q length vector, it's a vector in n-dimensional space. You look at this line, it's a 1-dimensional line. Look at the projection of the vector on this line. It's essentially this. It's just the inner product of the Q length vector with the all-mass vector. And look at the error after projection. So Q perp is defined to be the error. So it's the value of Q in the orthogonal direction to this line. And essentially we show that in the epsilon scaling, this goes to Q. The Q length from a single server queue we know should blow up as 1 over epsilon in the heavy traffic, right? And but the Q perp when multiplied by epsilon is going to, which means it's negligible compared to compared to parallel component. This is the sense in which we have to yeah, so this 2-dimensional vector can be approximated by a constant. I'll not get into details of how we prove it, but at the end of the day, it's a Lyapunov argument and it should drift towards the line. So that's the heavy traffic result. Yes.
Is this similar to water equilibrium?
In what sense?
Like balancing the queues.
Balancing the queues. I don't know. Water equilibrium has some game aspect, right? There are multiple agents and so on. Here, there's no multiple agents. Yeah. But maybe there is some similarity. I was talking to Gugan yesterday. He mentioned about sliding mode control, which has a very similar behavior. So maybe there is that.
It's just that the max, you have this fact just because the max, the way you equilibrate the queue is taking over compared to the service time, which is not able to process fast enough. Otherwise, if the service time was bigger, we have still the diversity.
Correct. Yeah, service times are order 1 for each of them, but the arrival rate is order 10, so it dominates.
So at the end, it's like you don't serve, and it's just piling up because you choose the shortest queue.
Correct.
But I think there is some similarity because water equilibrium, each individual node chooses the best path for it. And the best path
Here is
the
the
short path. So you understand. It's just that you are making a decision being made by the individual.
I see.
Water equilibrium outcome is that the delays are identical across all the equilibrium paths. So, which is sort of similar.
Similar,
to
yeah. So water equilibrium is
The ones that are safe, the roots that are safe,
Yeah. Here I think all of
are
that.
safe.
I see. So water of equilibrium also has arrivals and departures, or is it only, is it like
we use it as flows of water.
I see.
So now individual going here and sitting there.
I see. I see. Okay, cool. So that's with heavy traffic. Let's move on to the next one, mean field. Here the idea is I pick the load, need not be close to 1, you can think of it as half if you like. But I scale n, I let n go to infinity. This is like a large scale system. So this would be a very good approximation to study today's data because the number of servers is very, very large. And here the behavior is as follows. So in the limit, as n goes to infinity, this is what happens. There are no queues with queue length 2 or more. I mean, this is the limit. And the bunch of servers that are idle, the bunch of servers that are serving bunch. And the fraction of these servers is rho, and fraction of this is 1. This is the behavior in mean field regime for join the shortest queue. And this is work by my colleague Devang. Any questions on this?
You saying n row servers have one job and the rest have no jobs.
Correct.
Is that the
And then no servers have queue length 2 or queue length 3, queue length 4 also. I mean, if you look at the prelimit, there'll be like little of one servers with all of that, but in the limit, this is it. So nobody is waiting. So I come, there are these idle servers waiting for me, so this is me. Okay, now so there is a mean field here where there's no waiting for the customers at all, and there is heavy traffic here where the queue lengths are huge. I'm saying the queue lengths are like 1 over epsilon. Epsilon is very small, right? Of course, there is exponential distribution, but nevertheless, the scaling itself is huge. So then one can ask what happens in between, and that's where the many server heavy traffic comes. So in heavy traffic, I fix the system size n, let the load go to 1. In mean field, I fix the load, let the system size go to infinity. Here I can do both. So what I do is I pick my arrival rate. So in the heavy traffic, this was like n times 1 minus epsilon. Now I'm making this epsilon a function of n. So as I am becoming bigger and bigger, as the system is becoming bigger and bigger, I am also increasing. So that is what is happening here. And here, so my lambda is like this. This is like my epsilon. If epsilon does not depend on n, if it is basically a constant, that's kind of like alpha being infinity. You'll be in the other extreme, this extreme of heavy traffic. If alpha is 0, that means this whole thing is like some kind of constant, intuitively speaking. Then you are in the mean field, and you have all these regimes for various values of alpha. And so in the mean field, like I said, the bunch of 1 queues, the bunch of 0 queues, and nothing else. Here, queue length is huge, and you have exponential distribution. So let's go from here. Let's make alpha heavy. As alpha increases, the system is becoming heavier and heavier. I mean, this is all asymptotic. For each alpha, you have a different asymptotic regime, so to speak. And the system is becoming heavier and heavier as alpha increases. So from alpha equal to 0, as I keep making it larger and larger, my load, my rho, initially was a constant. Now it will become this 1 minus n power minus alpha. So nothing qualitatively changes. The fraction of 1 guys is going to become larger because the load has increased. But and the fraction of idles is smaller. But qualitatively, nothing has changed. It's essentially the same. And this continues until these idle guys become half, square root, alpha equal to half. Because when I say that in mean field it is like this is a very deterministic picture, right? But we have a stochastic system, it does have fluctuations. And from central limit theorem, we know the fluctuations are order square root of 5. But they're all hidden away in the limit. But the moment this idle guys become square root of n, then the central limit theorem fluctuations will dominate. And then because of that, there is some probability that the busy guys exceed the available number of servers, and then you will have waiting, and you will end up with something else. So you will basically, at alpha equal to half, you will end up having around square root of n servers that have 2 jobs, one being served and one waiting, and square root of n that are idle, and then the remaining that are that have just 1 job with the resistance. Yes.
Join the shortest queue. It seems surprising that there is a.
Correct. So what happened was when this guy came, this was all full. So he went and joined here. Now this guy has finished, so this is happening. So that is possible. So this is a first phase transition that happens as alpha increases, and this is called the half and bit. I mean, the half and bit studied NMQ, they didn't study JSU, But JSQ in this regime was studied by the sequence of things. Then now let's further increase the load. As you further increase the load, again qualitatively nothing changes. This idle guy is being squeezed out. Here it was square root of n. Now it is becoming less than square root of n. But this still remains square root of n. And this goes on until this 1 minus alpha becomes 0. You don't have any idle guys. That happens at alpha equal to 1. This is a second phase transition. This is called NDS regime. This was studied by Gupta and Walker even before happening. And what happens here is this is the first time when the Q lengths will start building up. Until this point, you had only 0, 1, or 2. But now you can actually have all possible. And once you go above 1, this Q length will actually start exploding. And you have to, the Q length will actually go to infinity in the limit. So in order to make it non-trivial, to get a non-trivial result, you have to scale it by an appropriate parameter. You have to scale it by n power alpha minus. For example, if n alpha equal to 2, you are scaling it by n. If you did not scale it by n, the Q length is actually going to. So here it is almost 0 or 1. Here it is 0, 1, 2. Here it is all possible values. Here it is. So this is the complete picture of LDS, JSQ, and then you can see there are lots and lots of references. So a lot of this work happened in the last few years. So yeah.
What is the equation for the alpha equal to 1 phase transition?
What's the intuition for alpha equal to 1 phase transition? Correct, yeah. So basically what's happening here is you have some idle cells, right? Going back to Guggen's question, whenever a job comes, if there is idle, it goes there. Otherwise, it will just become a second guy somewhere. That's it. Nothing else can happen. But the moment there are no idle servers, the non-linearity. If you think of queuing is almost linear. It's arrival Q length equal to arrival minus service, but that's not quite correct because you have this reflection at odds. It is A minus S bracket plus QK plus 1 equal to QK plus A minus S bracket plus. As long as you have idle servers, the bracket plus non-linearity is not equal. The moment idle servers disappear, non-linearity kicks in, and that leads to blocking. That's one intuition. This becomes 0, so you don't have idle servers, so you have this data.
Somehow it's like a constant gap from n.
Correct. Yeah, alpha equal to 1 corresponds to constant gap. Your arrival rate is order n, service rate is order n, the difference is constant.
Yeah, but then like the argument you gave for the can apply it to the narrow one that to the heavy traffic. So somehow the alpha equal to 1 is the constant gap.
Correct.
Results in some obstacle.
Correct. I mean, why does it happen right there? I don't have a better intuition. When you do some of these calculations, even back of the envelope, it kind of pops out naturally. But the only intuition I have is this: slab becomes so small that it can't compensate, and then the actual thing happens.
Will you not have an instance where like the Q length becomes more than 1, more than 2?
No, that's happening here. Here, Q lengths are actually huge. In the limit, they're going to infinity. And then once we scale it by appropriate parameter, like I don't know, n power whatever, then you'll have an non-trivial.
Below alpha, you will not have.
Below alpha, you will not. Below 1, you will not have. I mean, there'll be in the prelimit. This is all n going to infinity, right? In the prelimit system, you'll have some small probability of having 3 Qs, 4 Qs, and so on. But in the limit, the probability will go to 0.
So instantaneously, you may have, but probability is correct. Okay. So the number of tools should add up to n, right? So you have this n minus 2 times d10 that those.
I mean, these are all.
I mean, I understand.
Try to go. There should be bigos here.
Okay, but can you identify the constants as?
That I'm not sure. There are bigos. Can you get the constants? It's not my work. Like I said.
And yes, what is happening there? What is constant? Like number of.
Service rate is n. Arrival rate is n minus 1.
And then what is this in all possible Q values?
Which means here you had only 0, 1, 2, right? At NDS you'll see Q100, Q200 every value.
But the only way for us to change things a little bit, so variance, so constant maybe difficult.
Yeah, that's what I think, because these are all process level convergence results, and usually I don't think they can get confused, but you know, let's see. I don't want to say something. Yeah. Yeah, usually when I have these questions, I just knock my next door neighbor, then after this, my next door neighbor. Okay, good. So I know there was a lot in the previous slide. I think this is a summary that I want you to take away. This is alpha equal to 1. We'll only focus on this side. So Devankur and I decided that I'll be on this side, he'll be on the other side. So we'll only focus on this side, and on this side, the thing is you have to scale the QLens. QLens are going to infinity. You have to scale it appropriately. This is the epsilon in this case in circles. And after scaling, you'll get exponential. And on the other side, it is 0, almost 0.
I'm sorry,
What I mean is that if you just look at the QLens, multiply. No. So I'm just changing the arrival rate in the standard. As n goes to infinity, I'm approaching heavy traffic. If I just look at the QLens vector, it goes to infinity.
Okay.
Now to get a non-trivial limit, I have to scale it appropriately. I have to scale it. Then you get non-trivial limit. So this is the mini server heavy traffic again. I mean, this is the complete picture, but I think this picture is good enough for us because I only focus upon one for this for today's. I'm going way too slowly than I expected. So I'm going to skip a bunch of slides from how we prove some of these results. But maybe I'll just say one thing. So I said that the behavior is similar for all alpha greater than 1, but this was proved only for alpha greater than 2 in the literature. That's actually my work with my former student Daniela. And between 1 and 2 was open until our recent work, where jointly with Fakir, we actually showed that between 1 and 2 there's no qualitative difference. So there's no phase answer true. It's just that our earlier proof techniques were not enough to get this result. And the reason for that was the following. So at the end of the day, it's all about understanding the state-space collapse. And we in the past, we looked at the state-space collapse literally in this sense. You do this projection of Q4, and we take the norm, and we were working with 2 norm. And when we were working with 2 norm, somehow it didn't let us go beyond alpha equal to 2. It didn't let us go below 2. And turns out that instead of working with 2 norm, we have to work with infinity norm. Why? Because if I have a vector, let's say I have a vector that's like this, bunch of 1s and -1s, let's say half. The infinity norm of this is just 1, but the 2 norm of this is very different. So if I say that if I bound my 2 norm by some value, then it's a bigger set. But if I say that I can bound the infinity norm by a constant, then that's a stronger statement. Infinity norm bounded by 1 implies 2 norm is bounded by square root of n, but the converse is constant. So, and this way we can get a lot stronger handle on the state-space collapse. Essentially, what I'm saying is that if I show that infinity norm of the curve is less than 1, let's say, essentially what I'm saying is that all the QLens are almost equal, they're off by 1. But if I say 2 norm is bounded by square root of n, then it allows for many more possibilities. So, okay, this is the intuition, but at the end of the day, we have to work with a Lyapunov argument. And infinity norm is not a good Lyapunov function because it has max, and max means there are cases, and you can't really work with it. So the way we overcome it is as follows. And at the end of the day, I mentioned we are using exponential Lyapunov functions. So I need to work with something like this, e power infinity norm, and that is too hard to handle. So we end up working with an approximate version of it like this. So if theta is large, this is going to be approximated by this is a maximum value. Sum is same as the max for exponentials when theta is large, and so these two are kind of similar to each other. And this is a very nice function. We can just sum a bunch of nice exponentials, and this actually we show will work as a nice function. So that's all I want to say about these things. Any questions?
Can you tell me why the minus is some?
Which minus? This minus. Because this is Q perp, I'm subtracting the average. So some guys will be below average, some guys will be average. Okay, good. So, yeah.
You say that for these problems, what you mentioned, you know, even translate it as you don't have to scalar project available anymore.
That by itself is not an issue. I mean, that can potentially be issue. Indeed, that's true because some of the results we use Pythagoras theorem and so on for this. We don't have it in other norms, but I think that can somehow be handled. But the more serious issue is that if x infinity is 5, let's say, that means this one particular, maybe the sixth component is equal to 5. But at the next time step, if I say x infinity is 6, some other component may be 6. The identity is changed, and that is much harder to do.
And you could not have just tried to cook a norm of, you know, you start with the product scalar of like with the matrix A, like X transpose AX.
All possible is.
Yeah.
We didn't try that, but at least intuitively, I don't see why that will help because that will not get around this one square root of an issue. And we have symmetry anyway, so I don't see why a different issue.
So you could have seen an improvement in the argument. They use the fourth comment, for example. And the alpha, if you see the proof, they use the fourth comment, second comment.
For the
If you improve the alpha from 2 to a smaller one.
yeah. Actually, we did that. After doing all of them, we went to 2. So even though I mentioned the second moment, our method gives all the moments in one shot. So instead of using Cauchy-Schwarz at some point, if you use folder, you can get these higher moments, use those bounds, and optimize over those.
Not give you an improvement below 2.
If you did not do that, you would be at 3. By doing that, we went.
You want to focus on that.
I mean, we didn't stop at 4. We went till whatever. Yeah. Okay, good. So this is a summary. In unit traffic, it was exponential. In mean field, it was this almost 0 q lengths. And then in between these two, also there is this whole story, and there is the space transfer one, and we have expansion. Okay. Now let's go to large deviations. I want to quickly move on. So here the question is, I'm interested in the scale. And in large deviation, one looks at a quantity like this. Essentially, what this is saying is, suppose my tail is exponentially decaying. What is the exponent? This is just a fancy way of saying that in the limit as it's supposed to be. That is what large deviation theory looks at in this specific context. I mean, I'm looking at the many different ways in which people do large deviation results. Rajesh is an expert. I'm just looking at this scale large deviation things. Now, in a single server queue, like I said, you don't need any fancy theory. You can just take the steady state distribution, write it as e power log lambda, then you essentially get this, which means the answer for the large deviation question is log 1 1 lambda. The large deviation exponent, the Q length decays exponentially fast, where the exponent is log 1 1 lambda. And I can see this just from the stationary distribution. I don't need to prove anything. Now the question is, what happens? What is the large deviation exponent in the case of J's cube? And this was actually studied back in 2007, and it would prove that the large deviation exponent is simply log of 1 over log. And our result also essentially implies this, and we're going to see this.
Yeah. So these view fits to 1.
Yes, but that's not. Okay, so this is the large deviation, sir. So again, here you get the entire distribution in the limit. Here you get the entire distribution in the limit. Here, n and epsilon are fixed. So you're not looking at the entire distribution. You're looking at the tail, the asymptotic tail. Okay, good. So now let's jump into the non-asymptotic analysis. In fact, for non-asymptotic analysis, I also wanted to talk about some prior work. I think I'll skip that and just jump into my results. Because we are running out of time. So this is the setup that we look at. I just want to make everything concrete before I say the theorem. So this part, nothing has changed, and I'm focusing on mini server heavy traffic. You can also get this result in the classical heavy traffic, which means epsilon is the function of n. But just let's focus on mini server heavy traffic. And I'm assuming this alpha greater than 1. And alpha being infinity kind of corresponds to the classical heavy traffic. And the heavy traffic parameter epsilon is this guy. This is the 1 minus slope. Epsilon is simply 1 minus slope, it is n power minus. And the question we are trying to answer is, what is the decay rate of tail power? Right. So maybe I want to show just one slide before getting here. There has been a lot of work in recent times on science method, including some of my own work, where we show that, so I said that in a heavy traffic, you converge to exponential. With science method, you can characterize this rate of convergence in various distances. Here I'm showing the Kolmogorov distance. Kolmogorov distance is just the distance of the tails of the CPDFs, complementary CDFs, or the CDFs doesn't matter. And so we proved in our prior paper that the distance, this is simply exponential with mean 1. This is my tail of the total field length. And then we proved the distance between them decays like this. As epsilon goes to 0 in the classical heavy traffic, or for that matter, even in the mini server heavy traffic, this goes to 0. Now, if I'm interested in this tail, what I can do is I can use triangle inequality, send this guy onto the other side. And this is simply the tail of exponentials with e power minus x. So if I'm interested in the tail, this is a bad part. Because if x is large and epsilon is not too small, then this guy, my error term, is completely going to wash away my tail. So what I'm trying to say is distances like Kolmogorov distance and Wasserstein distance, bounds in the prelimit, in the non-asymptote, are not sufficient to get tail bounds. We need something more. And the question we are interested in is, if I'm interested in this tail, can I get an exponentially decaying tail without this additive constant? That is the kind of question I'm interested in. And that's what I'm going to state now. This was the theorem I showed before. Now let's parse this. So this is what I told before. I'm in this many server heavy traffic regime with alpha greater than 1. And I look at this tail. I have an upper and lower bounds that are exponential form. So this already answers what I showed in the previous slide. I want an exponentially decaying tail. And but then there is this caveat. I say that I don't have any limit in the statement. That's true. But then this guy has to be small enough. I mean, in the limit, this will go to 0 actually. When alpha is greater than 1, if alpha is greater than 1, this guy goes to 0 in the limit. But my result is pre-limit in the sense that I don't have to go to 0, but it has to be small enough. The small enough we have exact constants that show up there. Then the exponents are same for the upper and the lower bound, but the pre-exponents are clearly different. So in this sense, the exponents are the same. So if I look at it in the large deviation sense, so large deviation sense means you take the log of this probability, divide by x and take the limit. As x goes to infinity, these pre-exponent terms don't matter. The exponent term is what matters. And since they match, this recovers the large deviation result that I showed before. And this theta n indeed matches the 1 over rho. I mean, these are different notations, but if you actually look at it, this theta n is like the 1 over rho. So we recover the large deviation results, but there's a caveat. The large deviation result was for any n. N need not be, this thing need not be small enough. For me, this needs to be small. So I don't completely recover the large deviation result, but I recover it to some extent. But on the other hand, my result is a prelimit. So if I don't take the x to infinity, I still have upper and lower bounds of the tail. And I mean, you can visualize it something like this. So you take this tails and then take the log and divide by x. As x goes to infinity, this upper and lower bounds meet, but I nevertheless have bounds for all values. So in this sense, it's a non-asymptotic large deviation result. But the negative side of our result, the weakness is that it is only applicable when it is large. Yeah, so I forgot to tell you what the theta n is. It looks like this, and one can show that if you do the math, this is indeed the log 1 over log 1 over. So I showed how this result kind of recovers the large deviation result. Now I want to show how it recovers heavy traffic result. So in heavy traffic, I'm going to let n go to infinity. If n goes to infinity, it is easy to show that this term goes to 1. In fact, it goes to 0. So you can forget about this term, and this term also goes to 1. So these two terms match, and then one can show that this theta n actually goes to 1, which means this guy converges to this becomes e power minus x. And remember, in heavy traffic, my distribution is exponential with parameter, so it is e power minus x. So in heavy traffic, if this term was not there, I'm getting whatever I expect, e power minus x. But unfortunately, I have this term, and in heavy traffic, it's not going anywhere. It's not disappearing. In this sense, I'm not able to completely recover heavy traffic results, but I'm almost there because this is a pre-exponent. And we're currently working on getting rid of this. I think this is an artifact of our proof. I don't think this should be there. But if I talk about the proof, I'll tell you more about this. And not only that, I told you this converges to 1 as n goes to infinity. That's true. But not only that, we actually have the exact formula for this. So it is of this form. And prior work showed that the error with respect to heavy traffic. So if I forget about the 1 and if I ask the higher order term, prior work showed that it is of this order. This is what I showed you in the earlier result that talked about the convergence distance. But what we have now is actually tighter. So it can be shown that as epsilon as n goes to infinity, as epsilon goes to 0, this a goes to 1. But not only that, but the higher order term is smaller here than this. So our result also improves the rate of convergence to heavy traffic in the literature. Any questions? I know I've been telling many things, but the bottom line is that we have tail, we have upper and lower bounds that are true without any asymptote, and these almost recover the large deviations and almost recover the heavy traffic. That's the data. Okay, very good.
Lower bound. Exactly. For me, where I'm stuck, it's a lower bound.
Oh, okay. Lower bound is very simple. You can show that
just
single server.
the worst thing.
Yeah, that's it. Yeah. So going back to this picture, these were the asymptotic results from prior work that I talked about. We can think of our result as fitting somewhere in between because it almost recovers large deviation, heavy traffic, and all this many server heavy traffic up to alpha equal to 1. So in some sense, we sit in the interior of this triangle in this picture. We cannot get mean field with this at this point. So mean field is clearly outside. I mean, this is a very vague picture. You should not take it seriously. Say atom. And our bound looks like this. Yeah, so in this picture, like we get non-asymptotic results, but they're for large enough n, so we are not really there at any particular value of load and service level. But if they're large enough, we are here, but we don't recover mean field, so I highlighted this thing. Okay, good, lower bound. So it can be shown that, in fact, if you look at this lower bound, this theta n is of this form. If you substitute this theta in log, e power log should, e and log should kind of cancel. If you do that, if you simplify it, the lower bound looks like this. This is actually geometric randomness. It's a tail of geometric randomness with appropriate parameters. And we know that the steady state distribution of single server Q, MMR is geometric. So this is actually not coincidence. The way we prove the lower bound is that let's look at a system where you have a single server with capacity, with service rate and sum of all these rates. And then jobs, there is no load balance. Jobs simply going to this, the arrival rate is same. We can use coupling to show that if the service randomness and the arrival randomness between these two systems are coupled, we can show that sample pathways, this is a lower bound on this. Therefore, even without coupling, is the steady state distribution of this should be a lower bound on this, and the steady state distribution of this is that's how we get the lower bound. Yes.
Does it work when the normal vector is not on 1?
Yes, it works. Yeah. I mean, if it is all mu, it's the same thing. If they're different, also it works.
Because you don't say the mu, the mu which you say.
I mean, there is no. This is for every n fixed load. This coupling is true. Then you can take whatever limit.
You say lambda and you say on n. Okay. So at some point the mu doesn't count anymore because you're in the traffic.
No. He was asking if the coupling is true for different loads. Okay, the intuition here is very simple. This system is non-ideal, right? What that means is that as long as there is work in the system, there is no service that is basic. This system is ideal. Why? Because there could be some servers that are idle, whereas some jobs are waiting. We saw that in physics when there are 2 jobs. So that's why there should be 4 occurrences. That's it. More questions?
Are these difference dependent on the KSQ or are they applicable to any worker in the week?
So many of these results can be generalized. In fact, in the picture I showed you for the mini server, the phase transition and so on, the story is true, but the actual place where the phase transition happens can depend on the policy. So in fact, in our work on the space transitions and so on, we look at not just JSQ, we look at power of D. Power of D means that you sample D queues at random and send to the shortest among them. And now D can either be constant or it can scale with n. And under all these cases, we can look at like where the transition happens and so on. So qualitatively, the results are same, but the quantitatively different.
On the practitioner, what kind of question is this? Because the heavy traffic, the practitioner.
Practitioner.
So,
Good.
I understand that perhaps you only have 3 heavy traffic mean field.
Among the 3, mean field is probably the closest because data set is so huge.
So this one I understand. Heavy traffic.
Heavy traffic is
it's kind of
no system. No one wants to operate the system.
exactly. But it can happen, right?
Yeah, once in a while. This is like the worst case.
Exactly.
Heavy traffic is kind of like worst case.
And
Large deviation is also kind of.
in your case, you are what kind of application? I guess you have solved about it at some point.
Didn't have any application list slides exactly for this reason. I mean, okay, my viewpoint on this is that, like I said earlier, I want a bound on the Q length on the stationary distribution. I can't get that. So these are 3 various viewpoints, and this talk actually shows how each viewpoint has some value because they're all playing something together to get the bounded term. That is my thing. But if you just look at heavy traffic by itself, I would say it's not useful.
No.
All my work is heavy traffic, but I can't see that it's not useful. More questions?
The lower bound is one of the Q's closer. Can you go to the lower bound?
Right. Sorry. This is the proof. So I'm saying that I can construct a single server queue with service rate n.
For the lower bound.
This is for the lower bound. Yes, yes.
Upper bound is
Upper bound, I haven't talked about. Good. So the point of the upper bound is how much do you actually deviate from the single server. And now the state space collapse also kind of makes sense. State space collapse says all the queues are same. So remember I said that the point of this lower bound is that this is never idling, but this is idling. But if all the queues are equal, there's no idling. Because why is there idling in JSQ? Because I have 2 jobs waiting, but Guggen is idling. So that is wastage. But if I say that all queues should be equal, you have 2 jobs, he should also have 2 jobs, intuitively speaking. Therefore, he should not idle. So that's why state space collapse means that the behavior should be similar to queue. So the whole point of getting upper bound is how much do you deviate from. So you have to come to carefully characterize how much you deviate from state space collapse, and that's what is going to show up in the upper bound. So in fact, this term we had in the upper bound corresponds to the state space collapse range. So we can quantify the deviation from the all ones vector from the line, and that shows up in the upper bound. And this theta n is same as the single server because I said in the lower bound you have the same thing. So the large deviation exponent is same as the single server here, and this is the error I'll get. So the key again is transform method. I mentioned before, we use the same transform method. And to recap, the idea was that I use a Lyapunov function, exponential Lyapunov function, and set its bit to 0. That's what I explained to you in the context of single server queue earlier. Now for this system, what I do is I look at the sum of the qubits and then look at the exponent of this. Q here means sum of the qubits. It is e power sum of the qubits. Set its bit to 0. And then do, now there is no limit or anything like that because I want to prelimit yourself. So once you do this and then you kind of do some algebra, like go through the math, essentially you get a bound that looks like this. Let me pass this for you. So my Q length in this region should be scaled by this parameter. So this is appropriate scaling parameter. Theta is just the variable in the MGF. So this is essentially MGF of the scale Q. So I'm saying the MGF of the scale Q length is equal to, so this is not inequality and there is no limit. It's exactly equal to. This guy is the MGF of scaled geometry. If you had MM on Q with the service rate n, it would have stationary distribution geometry. And I'm scaling. So this is the MGF of the scale geometry. So if I was exactly like the lower bound, I should stop here. And that's it. I wouldn't have this. So this term in some sense captures my deviation from single term. And what is this term saying? This literally corresponds to this idealness I was talking about. If it so happens that if my system is such that either all queues idle or all are busy, then this term will be equal to 0 because this is saying one of the queues is 0 and there is sum of all the queues. If one of the queues is 0, if that implies all the q's are 0, that is what work conserving means, then this term will be 0, so the whole term will go away. But in reality for JS2 this need not be true. It is conceivable that Guggen is idling, so this indicator is 1, but there are q's, there are jobs in the system, so this q is not true. So the whole term indeed is present. For the limit results in our prior work, we showed that in the heavy traffic limit this goes to 1. So basically this is the only thing that matters. Now what we do is we basically quantify what this is. This we show using our state space collapse result and the bound on it and using the infinity and all of that stuff. We get a very strong, very refined bound on this term, and we show essentially that this is of its form, and this is exactly the pre-exponent term we have in the upper modulo the 2ex, which I get.
This one is also goes for general normal vector or
general normal vector? No, if the mu's are different, nothing changes. The state space collapse is still the same space, and everything goes through. The only reason we don't do it is when n is going to infinity, having mu's different is like the model becomes more complex. In the classical heavy traffic where n is fixed, we do that. We don't assume mu's. Okay, so I'm just formally stating this, that the same equation is formally stated here, except that I'm adding two things. One is that this guy should be small enough. If this guy is not small enough, this term is blowing up and that is bad. That's the reason we need it. And the second thing that I need is the theta. Remember I said this is the MGF of exponential. MGF of exponential, theta is defined, MGF is defined only just in a interval for theta. And the theta, that interval turns out to be this, where theta n is indeed the right rate, the decay rate, the large deviation explanation happens. So all I'm saying is this equation is true. I want to point out the two limitations of it. One is this guy. The second thing is the theta should be in an interval. Okay, and both of these are going to play a role. The first one is, why do we need that this quantity should be small enough? This picture explains this. The x-axis is same as the x-axis, the alpha of the mini server heavy traffic. Y-axis I'm taking n. So n is going to infinity as like along this line. So what I'm saying is at alpha equal to 1, there's a phase transition. So forget about this region, we can't even talk about it. Now, if you are in the region above this, here qualitatively you have the state space collapse onto the line. But the state space collapse is good enough only above this curve. Below that, the state space collapse is not strong enough. At least we can't get a handle on it. And that's the reason our result is only applicable above this curve. And that is where this n power 1 minus alpha log n is formed. So that's the first thing. Let's still remember that theta is in this interval, that is going to show up now. So far, what did we get? We got a bound in the NGF of this cube. I want tail bounds. If you have the NGF, I'll simply use Chernoff bound. The Markov inequality with the exponential Chernoff trick. That's all I'm doing here. So the tail probability is the Chernoff trick. Raise it to the exponent on both sides and use Markov inequality. And there's a theta parameter. The theta can be arbitrary. But since this result is only true for theta in this region, I have to minimize this upper bound over theta in this region. Okay. Now I substitute this here, and then I end up with this guy. Remember, this is MGF of geometry, scale geometry. And this is just the, I'm essentially trying to get, if I give you MGF of geometry, can you give me a tail bound on it? I mean, if you have geometric, you know exact tail bound, but instead of inverting the transform, if you use Markov inequality, so the tail of geometric with appropriate scaling should be equal to this. But because I'm using Markov inequality, which is not tight, we end up with this additional 3. So this is the source of the 3 exponential, which we believe should not be there. And there are other ways that we're exploring to get results. Any questions? So this is, I showed this before. We have this pre-exponent term, which I believe is not right. We have the tail bound, which is not only the large deviation but also the prelimit. And we have this term which captures the state space collapse violation. The nice thing is that the state space collapse violation does not affect the exponential term. It doesn't affect the large deviation. It only shows up in the pre-exponent. That's why it doesn't show up in large deviation. I'm almost out of time, so I think I'll just conclude. I think I just have a slide. This is just a result. I just wanted to flash it again. So to conclude, To conclude, we talked about the three asymptotic regimes. Classically, each of the results in all these regimes was obtained using very different tools. And using transform method, we're able to get prelimit results. If you get very precise prelimit results, you should be able to get all the asymptotic results from it. Our results are not that precise. That's why we're only able to reproduce large deviation and heavy traffic, but not mean field. And even in these two cases, we have limitations, like the pre-exponential and the heavy traffic, and then the large deviation kicking in only for large L. So future work includes if we can get rid of those two limitations, and if we can push it further, and if we can explore other systems with it. So with that, I want to conclude, and I want to thank Prakir, who made all these beautiful slides. Or another way of saying this is, if there are mistakes in the slides, he is to be blamed. Any more questions?
Didn't follow the transform method completely, but if you look at the application of it is not found.
Yes.
If you want to do this for now, independent, that is, of course, the product that you can take.
No, we are actually not doing that. Think of this as a single variable. Q is sum of Qs, sum of Qis, but think of it as a single variable. The fact that they're not independent does not show up. So if I give you a single random variable, that's exponential, then you know that, hey, you know everything. But what I'm saying is, let's start with the NGF, use the Markov inequality of the NGF, then you'll get a tail that looks like this, which is suboptimal in terms of taste. That's all it's.
But the NGF computed itself
that we already have. We essentially have that the NGF of this is equal to that of geometry. Modulo this term, this just comes out. This doesn't happen.
And somehow the NGF of the gamma and theta is the NGF of which system?
Gamma and theta is NGF of scale geometric. In the limit, this geometric is equal to exponential. So the problem is very simple. This is probability 101. If I give you NGF of exponential, you can invert the NGF to get the tail. That will be correct. Instead of doing that, if you use Markov inequality of the NGF, you will get this additional errors.
That's okay. But be able to write it in this particular form, that's where the dependent of the Q1, Q2, etc.
This is where we are exploring step forms. Because all the Qs are equal, it's as if you have a single Q that's giving this geometric NGF. But then in reality, you don't have single Q, you have this error from certain deviation
from these things.
that is captured.
The reason I'm bringing this up is the way in which it could be addressed, for example, in the book by Schwartz and Weiss. They have a book on deviations. They don't address it drawing for the school because I think the kind of thing that they address is Q1, Q2, Q1 plus Q2 to the Qn. But then independence is lost.
Yeah.
But if the independence is lost, there is still some structure.
Yeah.
Then you can maybe some continuity in the way in which then you can transform the independent to the non-independent system to a sort of transformation. Then I think you'll be able to capture the exponent consequence. The issue with drawing the process is that there is the continuity problem. The drift is that one angle on this side, Q1 is higher, different angle.
Right.
So at the boundary, there is discontinuity of the drift.
Correct.
That's the issue where that's the reason why their method is not applied. So whereas here, somehow you got around that.
Yes.
To another.
I mean, we are completely different, right? We are not using any of the usual large deviation theory. We're not using the Grassano,
but it works for Q1 plus Q2 plus Q1.
Yes. But like I pointed out, this is a paper from 2017 or so where they actually do this. Get the large deviation circles.
So yeah, once these results for the first one that handled the discontinuity in a different way. I don't remember the
I don't even know how they did. We just did literature survey after we had the result. I'm not an expert in large deviations as such.
So somewhere hidden in that correction from state space collapse from this.
Correct. That's why we had to do most of our hard work is in state space collapse, getting this product form thing and showing all the state space collapse errors here. That's somehow the key thing.
You also said that you use power of deviations rather than kind of this. So did the transition points depend on
Yes.
whether you use JSP or power of deviations?
Correct. So
The choice of D.
yes. So I think if I recall,
If you don't have it properly, then you go to then you go to the shortest among.
see even in GSQ there's no decoupling.
But
that's
then
not-
the one that was
Or there is
Okay, so I'll tell you what it is in power of D. So if D is constant, it's this transition instead of 1, it should happen. But we didn't quite prove that. That is yet to be done. I think this is true, but we haven't written it down because I said that before this paper, we only knew this result up to 2. At that time, if D was constant, we had it up. If JSQ is at 2, power of D was at 3. Now that JSQ improved to 1, that should improve. That's fine. Now, if you scale D with L, then if D is like n power beta, for example, that beta will show up and we have that also, that characterization. It's 2 plus 1 over beta or some such thing. Yes. As beta goes to n, this reduces to this.
one layman question. For a practitioner, does it help me determine the probability of a drop if I am considering a fixed Q size?
Yeah. So I think the only limitation at this point is the condition that n power r n should be large enough. I think if you have a large enough system, then you can definitely use these bounds. But I guess if we are able to further improve this bound so that I can remove that condition, then I think this is as close to practice as it gets, I guess. Because this is giving explicit bounds.
How can you generalize this to examine from applications point of view? If you could recover some of this, say you have 2 types of variables, both Poisson. It's a different reach but different service requirement. Say a class of variable that require for this time is very exponential but very small as compared to the other class.
Yes.
In those scenarios, even MM1, so like average delay seen by one class versus the other, both kinds of things are different. Could you use your transform method for it?
Okay, very good. So at the heart of the result that I showed you is this state-space collapse, right? Because of the state-space collapse, everything boiled down to a single server queue. Then I was able to do this product form decomposition also. So now not all systems need to have that. So you could have a multi-dimensional state-space collapse. Then does transform method work? The answer is yes. But in fact, actually, we developed transform method in my group to solve that problem. This came as a side thing as a development. But we haven't done prelimit results. We only have limit results for that. And even the limit results are not completely done. We have a paper, in fact, I gave a talk in CLA seminar virtual last year, where so what I said was in single server queue, if you do transform method, the MGF of exponential just pops out. You don't have to do it. But in the multi-dimensional case, instead of getting the MGF, you get an implicit equation in the MGF. In the MGF, so if you have collapses with a cone, the MGF of the probability distribution of the cone and the boundaries, this will show up as an implicit equation. Now you have to solve that implicit equation. And solving these implicit equations is very hard. They relate to boundary value problems. What we were able to do is we looked at a specific system, 2 specific systems, N system and switch system. There in N system, we were able to solve it using some framework. In the switch system, we wrote down the equation, we guessed an answer, plugged it and verified. Now, if you prove that it has a unique solution, you're done. But we are struggling with that. Bottom line is transform method is powerful. It gives many different things. We were able to get many different qualitative results in transform method. I have some work on load balancing with abandonments, which was also using that.
other probing question on how powerful it may be. Suppose I change it to, let's say, alpha, sorry, W1, Q1 to W2, Q2.
Yeah.
Greater than X.
Yeah.
Do you think that?
If you change the policy also,
Also, I'm still looking at joint Q.
I see.
But the sizes at which the costs associated with the Q sizes.
No. So if you have Wi and Qi, then actually if you want to minimize the costs, the right thing you should do is not join the shortest queue. You should equalize the W times Qs.
Policy is joined. I'm not minimizing the policy of
I see.
Wi Q.
So I can't do ASQ with that. If I change the policy, then if you change the policy to have the W, then
Reason I'm asking is again, I could ask the state of the queues, can it be like something, you know that it ought to be something, but can it be like something else?
right.
If you answer this question of W1 Q1 to W2 Q2 for all W1 and W2, you answer that question as well. And so somehow
Correct.
something
Yes,
special
yes,
about the Q1 plus Q2. Or
Yes.
in your case,
Yes.
the sum. Can you articulate what the
Um, So essentially, I think what it boils down to is, okay, actually now I'm confused. Maybe we can do that in GSQ case because at the end of the day, there is only one vector. Summation Wi Qi is just going to boil down to summation Wi times Q1 because all the Qs are equal. So it's essentially the same thing.
The correction is where most of the work lies.
Yeah, but I can observe this W's into theta. I think I should be able to handle that. But in the multi-dimensional collapse, I can't play these tricks because here you're sitting on a line. That's why all these things work. But if in the limit you have probability mass in the entire quadrant, let's say, then you can't do this. You need to somehow get a handle on the entire thing, and that's the challenge. That's where this implicit equation and this boundary value problems want to show. In fact, that's how we literally thought about it in this multi-dimensional case. I have prior work with Srikanth on getting expectation of some of the Q lengths in switch. Then I thought if I can get all weighted combinations of the Q lengths, moments of those, I have the distribution. Then we realized that the methods I was using to get the sum are not sufficient to get this. We actually have a negative result. Then we developed transform method, which is able to push things further, but it gets stuck at this boundary value.